will give the talk.
Yes, thank you very much. Yes, so I'm Sam McCauley. This is joint work with Jesper Nicholson and Rasmus Pei, and I'm going to talk to you. Good. Perfect. All right, I'm going to talk to you about set similarity search for skewed data. All right, so when I talk about set similarity search, we're going to look at a database of sets of items. I mean set in the mathematical sense, so I only care about which items are in the set. I don't care about how many times they occur or what order they occur in. So examples of this, you could have words of a document. Usually you pair them together into k-grams. It could be tags of an image. It could be movies seen by a user, something like that. So I take the book, I go through it, I look at all of the words, and I get this list, which is in no particular order. I can do the same thing with image tags. This is an actual image. These are the tags for the images. In both cases, this is just a set of things, which gives me some information about this image in this case. So in particular, the items in the set are drawn from a very large universe of potential items. All English words, all image tags, something like that. So we need to avoid the curse of dimensionality. So there are known algorithms that have running time something like 2 to the number of potential items. That's way too big for us. When I say similarity, we want to find another set in our database which has many items in common with the query. So these are both fantasy novels, and we can see in the list of words, obviously I chose this list, but many of these words are in common between these two books. Therefore, we think that they're fairly similar. So in particular, we're going to get our database of sets, and we want to pre-process this database so that we can answer queries quickly, where the query is, find me a set in this database which is similar to this query. And in particular, when I talk about pre-processing, we're allowed to use extra space to make the queries fast. A pretty decent amount of extra space, even a polynomial amount of extra space, actually. So set similarity search is a fundamental problem in big data. It's important for recommendations, computer vision, data deduplication, many other things. This is a Facebook news feed. Maybe you want to see what sort of things one person has looked at and compare it to what sort of things someone else has looked at. These are both sets. We want to find similar ones. And I want to say really quickly that our bounds basically just immediately apply to joins. So you can think of a join as being finding all similar pairs. And there's sort of a few papers that have looked at this, which basically the running times I talk about apply immediately. You just multiply everything by n. So I want to talk about two notions of similarity. So Jacquard is very popular, and it's used all over the place. Braun blanket is a little bit less popular. You may or may not have heard of it. But they basically do the same thing. So in both cases, on top, I have the number of items these two things have in common. So on top, I have the size of the set intersection. And on the bottom, I'm going to normalize this so that the similarity lies between 0 and 1. And the difference between Jacquard similarity and Braun blanket similarity is exactly how I normalize. So for Jacquard similarity, I normalize using the size of the union. For Braun blanket similarity, I use the maximum size of either set. So in both cases, these similarities are always between 0 and 1. Sounds good? If I have two sets A and B that have no elements in common, they always have similarity 0. And a set with itself, or two identical sets, always has the maximum similarity 1. So that's true for both of these. And so we're going to obtain results for both Jacquard and Braun blanket similarity using a reduction from Christiani Pei, a previous paper, which I'll actually talk about more in a second. But today, I'm only going to talk about Braun blanket for simplicity. So if you really like Jacquard similarity, every time I say Braun blanket, you can replace with Jacquard in your head, and that's OK. All right, so actually, let's talk about this paper. So this is a paper. It's about an algorithm called chosen path. And this is an optimal worst-case algorithm for set similarity search. So in particular, it improves or matches min-hash. It depends on exactly what your parameters are. And min-hash is also optimal. Right, so this is basically a competitor to min-hash that works in a slightly different way that we're going to take advantage of today. So the way this works at a high level, and in the next few slides I'll go through this in detail, we're going to sample items in the query set recursively. And we're going to call this bunch of samples a filter. Once we've sampled enough items, I'm going to brute force compare with all of the database sets that also contain all of these items. So I went through this whole book. I sampled 4 words from this book at random. I'll talk about how to do that in a second. And now I'm going to look through my entire database, and I'm going to brute force compare with every book in my database that has these 4 words. So maybe it looks like this. So again, I have this fairly similar fantasy book. I have Lord of the Rings, which is by the same author. It's very, very, very similar, and it's probably the most similar point that we're looking for. But because I'm just sampling a few words, sometimes things don't quite work out the way I want. So I'm also going to get, in this case, the Cambridge History of China, which is not very closely related to this fantasy novel. It just happens to contain these 4 words. So what I'm going to do, I get these 3 books, and I brute force compare to all of them to see exactly what the similarity is. So this is a matter of getting a smaller number of candidates that I will brute force against. So let me talk about how I'm going to generate these filters, how I'm going to generate these subsets. So like I said, this is a recursive process, so I'm going to start with the empty filter. The empty filter is, all books, all sets have this empty filter, right? I'm going to go through my words one by one. Obviously, there's more than 6 words, but I can't fit all of them on this slide. So each time I'm at a word, I'm going to flip a biased coin. So this isn't 50-50, but I'm going to flip this coin. I go to is, I get tails. I go to at, I get heads. That means I'm going to create a child of this filter, which has just the single word at in it. I keep going. House, I get tails. Hobbit, I get heads. So I create a filter which has hobbit in it. There, when the, I get tails for all of them. All right, so I've created one new level. I have a bunch of filters, each of which have 1 item in them. Now, I'm going to recurse. So I go down to the first child, I go down to at, and I start over. I do the same thing. I go to is. This time, I flip my coin, I get heads. So I create a new filter that has at and is in it. At, house, house, I flip the heads. So I create a new filter with at and house. The rest I get tails for the sake of time. Then I go back up and I recurse on hobbit as well. Is, I flip heads, and then I flip a bunch of tails. And I keep doing this down the tree until I hit a specified size. So in this case, I've decided that I'm going to cut off at size 3. So after I get to this 3rd level, I'm going to stop and say that I'm done. Yes, stop after a certain number of levels. And I want to say very quickly, these are completely independent. So there may be some redundancy here. So you can see these first 2 filters. We have at, is, and house, and then we have at, house, and is. These are going to contain the same items, but we don't want to spend time making sure that each of these are unique, so we'll just let that happen. It won't hurt our bounds on average. All right, so these are my filters. I'm just going to take these leaves. I'm not going to take the expensive ones higher up. And for each of these filters, I'm going to look through all database sets that also chose this path, hence the name. I should say really quickly, I was talking about flipping coins. When I'm saying that the database sets also chose the path, I need some consistency in this randomness. So we don't actually flip coins, we just use hashing. But when you look at a single set, it has the same effect. We're choosing things randomly, but we use hashing to randomly choose things in a consistent way. An important point to make is that a database set can only choose a path if it contains all of the elements in that path. Right? So when I'm looking at everything that goes down to this filter, it is exactly all of the books in the database that has these 3 words in it. So this makes pre-processing really easy. So when I want to pre-process my database, I just generate this tree for each database set. And then I just need to store reverse pointers so that when I get to one of these filters, I can look up what else got to one of these filters. All right, so so these are my filters, and I'm going to look at everything in each of the filters. Some of them are really big. At, is, and house, that's not very useful for us, right? I'm going to get tons of books from all over the place. Like I said, the second filter is actually even going to give us exactly the same books. They're both going to be really big. The 3rd filter is at least different, but it's also big. We got unlucky. But then the next 2 are really good. They happen to contain this really rare, made-up, in fact, word hobbit. So they each contain only 1 book. And they, in fact, each contain our similar point, which is really good. So I have some bad filters and I have some good ones. On average, it's going to do all right, though. So let's talk about some parameters here. With what probability do we sample an item? How biased are these coins? And then, how far do I go down the tree? 3 seems sort of like a bad choice. How far do I actually want to go down? The answer to the first one is we're going to set this probability so that we have one survivor in expectation. Right? So at the beginning, at the very top of the level, I know that if I look in this empty filter, I'm going to find my close set. I want that to be true every time I recurse down this tree. So I'm going to set my probabilities very carefully so that each time I go down a level, I still, on average, find this close point. And then the next question is, when do I stop recursing? And the answer is I'm going to stop recursing when the filters have expected size 1. Some may be a little bigger, some may be a little smaller, but on average they have size 1. If you do the math out, this is going to give you a small polynomial number of constant size filters. Exactly how small, we need an approximation factor. Let me just say exactly what the result is. It's if there is a set which has similarity at least B1 with the query, this is brown blanket similarity, I'll return a set which has similarity at least B2. And you get n to the log B1 over log B2 time. And that's just some constant. So this is chosen path. This is one way to solve this problem. So like I said, we may have some fairly big filters, but if you set the parameters right, your costs are moderate on average. They don't occur too often. The other way to do this is prefix filtering by Chowdhury et al. Now this is a lossless similarity search method. We don't have this approximation factor. We're going to go through the items, and we are going to look at all sets that have any of these items in common. Not all of them, any of them. But an intersection of size r means we can look at all but r minus 1 items. Let me go through this very quickly. So we go through my list of words in The Hobbit. I look at house. I find all of the books which have the word house in it. That's going to take some time. Journey, I look through all of the books that have journey. That one's not as bad. I look through Hobbit. One book has the word Hobbit in it. That's very good, very fast. And in fact, it only contains the close point. That's really good for us. Then I go to there, I go to win. Those are going to be terrible, very, very slow. But when I get to the very bottom, let's assume that I'm looking for a set with intersection of size at least 4. Just basic pigeonhole principle. We're going to need to have one black item in common with the query. We don't need to look at these red items, and we're still guaranteed to find all points with intersection size at least 4. So the good news is, even though we spend a lot of time on each of these, we can avoid looking at r minus 1 of these items. Which ones do we avoid looking at? Well, of course, we want to avoid looking at the most common ones, because those are the most expensive. And that's prefix filtering. That's the whole thing. Like I said, this can be very effective for some data sets. If you have these words like Hobbit that are very small and bring you right to the close point. In the best case, we may only need to look at a few elements, way better than this, quote-unquote small polynomial. But if the data set is adversarial, this can be very, very slow. So I should mention very quickly, this is only a high-level idea of prefix filtering. This is a big area. People have done a lot of work on making this faster and faster and on taking advantage of different types of structure, a long line of work on improvements. But this high-level idea of you're greedily ruling out sets stays the same. So I should say really quickly, these both sort of fit into something called a filtering framework. In both of these cases, we're going to have this subset of words. For chosen path, it'll be a bunch of words. But for prefix filtering, it'll just be one word at a time. And I'm going to look at all of my database sets that contain everything in each one of these filters. Once I get this list of candidates, I'm going to brute force compare with all of the sets in each filter. And the cost is just the total size of all filters, ignoring things like D, which I'll do for now. So really, we just want to have these filters be as small as possible in total. All right, so we have two methods for similarity search. Chosen path is optimal in worst case, but it needs an approximation factor, and it always has the same running time, even on easy data sets. I'm still going to spend all of this time generating all of these filters. Prefix filtering greedily searches for rare items, so it's extremely fast in some cases, but it can even be linear in the worst case. We need these helpful rare bits. What's even worse about this is that our only option right now, when you're deciding what to use, is you just run both and see which one is faster. And then you just use that one. There's no easy way to say, this is a prefix filtering data set, this is a chosen path data set. So this is our goal for today. The first question is, what kind of data has structure that we can exploit? When are things easy and when are things hard? And the second question is, how can we parameterize performance based on how much structure there is? And ideally, we want a smooth trade-off where we don't just have these two algorithms to choose from. We want, as the data structure gets harder and harder, our running time gets worse and worse. And as the data set gets easier, our running time gets better. This is our goal for today. So let's talk about skew. As we saw, some items in a filter give far more information than others. This can be rare words in a book, rare tags of an image. All right, so this is being videotaped right now. I assume that this video is going to have a tag that is something along the lines of PODS 2018. That's going to make it really, really easy for all of us to find, right? We also saw, of course, seeing the word Hobbit in a book also gives lots of information about what other books might be similar. So this is basically, this skew is going to be the basis of our quote-unquote easier distributions. So we're going to assume that the data is random, but from a skewed distribution. So each set is a sample of independent items, where some items are more common than others. That is the skew. That is what gives us our structure. And we have some initial experiments in the paper that some well-known data sets, which are really often used for things like set similarity joins, have this skew, and they have only very limited dependence. So they're somewhat close to what we're trying to model here. So we're going to consider two different models of queries. The first kind of query is piercing correlated. That's sort of a mathematical thing. At the end of the day, this means that the query is going to look like the rest of the data set. The probability of an item being in the query is the same probability it would be if it was one of these random data set items. So this is for when you're comparing apples to apples. You have a data set of books. You're going to be querying using books that are from that same distribution. The second model we looked at is adversarial. The query can be anywhere. So you can only take advantage of skew when you're pre-processing the data set. The query still might be hard. So in particular, the query might not look anything like the rest of the data set. It may have a lot of rare items. It may have a lot of common items. We don't know. So this is good when you're comparing things that are sort of two different types. The query may not be from the same distribution. So there's two sort of parameters that I was talking about for chosen path. The probability with which you sample points and how far down you go. So let's look at the probability with which you sample points. For adversarial, you have to sample uniformly. You have no choice. If you do one more often than the other, then the adversary will just say, ha, that's where your similar point was. But for the correlated point, things get a little bit more interesting. It turns out we want to sample proportional to the conditional probability of that item being in the close point. In other words, we know that this item is in the query. Conditioned on that, what is the probability that the item is also in the close set? So that's how, when I say proportional, this is how we decide what to sample more often than others. We're still going to scale all of them so that we get one total survivor in expectation, which is what gives us correctness. So remember, I went left to right through these items, and I decided whether or not to add them onto my filter. I'm going to do that again, except instead of flipping the same coin every time, I'm going to change the probabilities. Right? So Hobbit is super rare. I want to sample that really often, because it's going to get me a lot of information. So maybe I flip a coin for Hobbit. For House, that's okay, so I'll roll a die. It's a little bit less likely. But for words like is, at, and the, I don't want to sample them with very good probability at all. You probably can't say, this is a 100-sided die, right? So this represents the fact that you're not going to sample them very often. So this is how we decide with what probability we sample each point. The next question is, when do we stop recursing? And the answer is actually the same, when there's one item in the filter in expectation. But now, that means that the tree is uneven, because some filters are going to have more expected items than others. So you can see right here, this is the same tree as before, but when I get to Hobbit, I only have one expected item. I can stop right there. I don't want to waste time recursing and generating more filters that I'm going to have to look through all of them just to get the same information over and over. Once I see Hobbit, I say, I'm done. This is my filter. And that is going to be a leaf of my tree. All right, so that's the whole algorithm. The question is, what's the running time? Unfortunately, there's no closed form, and it's going to depend on all of the probabilities in the distribution. So this is a little bit of a mess. I'm going to summarize this on the next slide, though. So for Pearson correlated queries, we have these two big sums. I want to say just very quickly on the bottom, that is the conditional probability with which you sample a point. That's why that comes up there. I should also say PI is the probability of item I. Right? So you get running time n to the row, where rho solves this big equation. For worst case queries, you get a slightly worse bound. You get a slightly simpler equation. You just sum over all i's. So something I want to mention, by the way, is this is over all i's in the whole universe, right? This is I from 1 to D, where D is the the universe of items that the set is from. For the query, we only sum over the i's in the query. But that means that some queries give different running times than others. This kind of makes sense. Because if you have a query like The Hobbit, which has this rare word, which brings you right to your close point, that's going to take less time to look for than a book like The Cat in the Hat, which has nothing but very simple, very common words. Like this is almost an adversarial case. So for the worst case model, you actually get query-dependent running times based on how many rare and how many common things it has. So very quickly, the special cases for the running time. If there's no skew at all, if there's no structure, then we get the same running time as chosen path. Everything just sort of cancels in those equations before. If there are incredibly rare items with basically you only have a constant number of database sets containing each of these items in expectation, something like Hobbit, where you're only going to find one book with it, and then the rest of the items are very common, they occur with constant probability, then you get the same running time as prefix filtering. In fact, if you actually look at things, we almost do the same thing as prefix filtering. Because remember, I cut things off at Hobbit, right? Whenever I sample one of these rare items, I stop and I say that's my filter. That's a lot like prefix filtering, where you go through the rare items one at a time and you take them as a filter, each at once. There's some differences, but they do a similar thing and they get the same running time. And as I said before, we want an even trade-off. We want to do well in between. We're going to always do at least as well as either. And when the skew is moderate, we're actually going to do significantly better than both. So the conclusion to take away from this is that modeling the structure in high-dimensional data can give you non-trivial algorithms that take advantage of this structure. And it gives significant theoretical speedups for non-adversarial data sets. In this case, random data sets with a lot of skew. What I'm really interested in now is how fast is this in practice? So our analysis is a little bit loose. In practice, do we get something that's sort of like our analysis, where we get these n to the row like times, or is it actually really fast heuristically? We don't know yet. And then the second thing is, I mentioned very quickly that we have this independence assumption. This assumption is, in some ways, very, very bad, right? Words in a book are not independent. What songs you listen to on Spotify are not at all independent. What we don't know is, there's sort of two things. We don't know how much this dependence actually affects our running time. And it would be really interesting to see if you can build an algorithm that takes this dependence into account, where it cuts off a filter not just based on the product of the probabilities of the items in the filter, but also how they depend on each other, which gives you something a little bit more exact. But this is going to require some more insights. Thank you very much.
My question is, I just want to understand some intuition of this path-based filter construction. So why not just use like a random sample, like standard LSH, so you have a lot of filters. So why this path-based or tree-based construction is better than that? So it seems you have some correlation. So is this correlation helps this filtering procedure? Or?
I believe it does. I don't know if you can do it the other way, but I know that the way we show that this way works relies on the tree structure, because it relies on this inductive proof of if you survived so far, you should also survive at the next step.
But for for independent sampling, you can still do the same thing, right? You can do important sampling, this kind of thing.
I would think so. Exactly. I would be surprised if just starting at the leaves gives you different results. I would be surprised, but I don't know for sure.
I see. So have you compared? Like, have you analyzed just using like some random construction of?
I mean, and the thing, you're definitely going to get the same running time.
Oh yeah.
So in practice, I have no idea.
So this construction gives you better accuracy, or is this
the proof of correctness works for this construction. Okay. I would imagine that your construction is also fine, but I don't know for sure. And I'm pretty sure it wouldn't give different running time, which is why I haven't looked into it yet. But it could be a cool thing to look into in terms of implementation.
Okay. Thank you.
Yeah.
Let's thank the speaker again.